In the next video, we're going to talk about how to make alcohols from reduction reactions of aldehydes and ketones. But first, I wanted to talk a little bit more generally about reduction and oxidation. Now, you would have first learned about reduction and oxidation and redox reactions in general chemistry, right? These are reactions that involve transfer of electrons. So when we have transfer of electrons, we need some way of keeping track of where the electrons are going. We generally do that with oxidation states. Now, these may feel somewhat familiar to formal charges, and really these are both just two different bookkeeping techniques for keeping track of the electrons. Now, to determine the oxidation state of an atom, all of the shared electrons are given to the more electronegative atom. So basically the difference between formal charges and oxidation states, they're both basically fictitious. When we calculate formal charges, we assume that all of the bonds are purely covalent, and the electrons are shared exactly equally between the atoms that are connected by that bond. And we know that's not true, right? In the case of a carbon-oxygen bond, we know that's polar covalent, and the electrons spend more time around the oxygen than they do around the carbon. But when we start talking about like partial numbers of electrons, it's hard to keep tracks of things. So that's what makes formal charges useful. It's sort of one end of the spectrum. If all of the bonds were purely covalent, what would the charges be? Oxidation states sort of go in the other extreme. We treat all bonds as if they were ionic, and then all of the electrons go with the more electronegative atom. So these are sort of both fictitious, but both useful for different things. They're bookkeeping techniques to keep track of where the electrons are going, and they sort of go to the two extremes. In formal charges, we treat the bonds as if they were purely covalent. In ionic bonds, we treat the bonds as if they were purely ionic. But when we count up the oxidation state, once I've divided the electrons, it works just like the formal charge, right? In the case of methanol, right, when I allow the electrons to be shared equally, so half the shared electrons go to the carbon, the other half go to the other atoms, right? Carbon normally has 4 valence electrons. We've given it 4 valence electrons in this formal charge scheme, and so it has a charge of 0. And in general, we know that when carbon has 4 bonds, it has a formal charge of 0. In the case of methanol, when we think about its oxidation state, carbon is more electronegative than hydrogen, so it gets to keep all of the electrons that it would have shared with the hydrogen. But then because oxygen is more electronegative than carbon, all of those shared electrons from this bond go with the oxygen. So then carbon is left with 6 electrons. It normally would have 2, and so in this case, the oxidation state of the carbon is -2. All right, and so here we have a number of different compounds, and we can see the different oxidation states that the carbon has. And so in this case, right, carbon would get all of the electrons here because it's more electronegative than carbon, so it would get 8 electrons, and so that's 4 more than it would normally have in terms of valence electrons, so that has an oxidation state of -4. We showed on the previous slide that methanol has an oxidation state of -2. In this case, the carbon gets all of the bonds that it has with hydrogen, so that gives it 4. It loses all those electrons to carbon, so it gets 4 electrons. Carbon has 4 valence electrons, so when formaldehyde, it has an oxidation state of 0. And we can do the same analysis for the formic acid and the carbon dioxide. And so when we have reactions, it's an oxidation reaction if carbon's oxidation state is increased. In that case, oxygen has effectively lost electrons, right? If the oxidation state increases, it becomes more positive. So sort of as I go in this direction, these all represent oxidation reactions. If I went from methane to methanol to formaldehyde to formic acid to carbon dioxide, those would all involve oxidation reactions. If I go in the opposite direction, when carbon's oxidation state is decreased, that's a reduction reaction. That means the carbon is effectively gaining electrons. Now, we don't always have to go through and calculate the oxidation states to see whether a reaction was an oxidation or reduction or neither. We can sort of do it qualitatively, right? In general, the more bonds there are between carbons and more electronegative atoms, that will be an oxidation reaction. if I have less bonds between carbon and its more electronegative atoms, that results in a reduction. And so we can kind of see that when I go from methane, there are no bonds between carbons and electronegative atoms. When I go to methanol, now I have one carbon-oxygen bond. So I have more bonds between carbon and more electronegative atoms, so that represents an oxidation. Now I have 2 bonds to oxygen. That's another oxidation. Now I have 3 bonds to oxygen. That's another oxidation. Now I have 4 bonds to oxygen. That's another oxidation. When I go from carbon dioxide to formic acid, I go from 4 bonds to oxygen to 3 bonds to oxygen, so I have less bonds between carbon and a more electronegative atom. So going from carbon dioxide to formic acid would be a reduction. So I think being able to do this qualitatively is going to be even more useful to us than being able to calculate the oxidation states, which you still need to do, but it's much easier if you can quickly look at a compound and see, oh, right, when I go from formic acid to carbon dioxide, I increase the number of carbon-oxygen bonds, so that was an oxidation. Okay, so let's look at 2 examples. So first, let's just qualitatively determine whether the compound was oxidized, reduced, or neither. So in the first compound, I have 1 bond between carbon and oxygen, and I go to 2 bonds between carbon and oxygen. And so this appears to me that it was oxidized. Right, let's go ahead and assign oxidation states to see if we can confirm that prediction. Now, in the previous examples, we had all different elements. In this case, right, the carbon is bonded to 2 carbons. In that case, we do divide the electrons evenly. So we also have a hydrogen here, right? So the carbon is going to get one of these electrons. It's going to get one of those electrons. It'll get both from the hydrogen, and then it'll lose those bonding electrons to the oxygen. So it's going to get 4 electrons when I divide them up for oxidation states. Carbon normally has 4 valence electrons, so its oxidation state is 0. Right? In this case, the carbon's going to lose the electrons that it's sharing with the oxygen. It'll get 1 each from the oxygens, or from the bonds to the other carbon atoms. So it'll get 2 electrons. Right? Carbon normally has 4 valence electrons, so it's effectively lost 2 electrons. So it would have a +2 oxidation state. So when I go from 0 to something more positive, that is in fact an oxidation. All right, so one more example. So I'm going from this compound to this compound. And here I have bonds between a carbon and a more electronegative atom, and I have 2 of them. I have 2 bonds between a carbon and a more electronegative fluorine in this case. In this molecule, I have 2 bonds between carbon and a more electronegative oxygen. So 2 bonds to a more electronegative atom, 2 bonds to a more electronegative atom. And so in this case, I think it's going to be neither. The oxidation state of that carbon is not going to change. Right? In our first case, right, I've got a bond between the carbon and a carbon, and a carbon and a carbon. So it'll get 1 electron from each of those bonds. It loses those electrons to the fluorine. So carbon gets 2 electrons. It normally has 4, so that would be a +2 oxidation state. In this case, right, it gets 1 electron from that bond, it gets 1 electron from that bond, it loses all those bonding electrons to oxygen. So again, carbon gets 2 electrons, it normally has 4 valence electrons, it has a +2 oxidation state. So the oxidation state of that carbon did not change, and so it is in fact not a reduction or an oxidation.